Welcome back everyone to part 3 of our supervised learning project. And what we're going to do now is explore 3 different tree-based models, a single decision tree, and then we'll also explore random forests and a boosting method such as add-a-boost classifier. Let's head back to the notebook and continue where we left off last time. Okay, here we are at part 4, predictive modeling, and we're really going to be exploring 3 main methods, 4 in total. First method is single decision tree, next is a random forest, and then the 2 boosting methods, adaptive boosting and gradient boosting. And as we keep mentioning, feel free to add any other supervised learning models for classification like support vector machines or logistic regression and see if they can actually improve on the performances of the tree-based methods. We're using the tree-based methods because we didn't really get a chance to exercise our skills with them in the previous tree-based methods lectures. So what we first need to do is separate out the data into X features and a Y label. Now, if we took a look at the data itself, we have a wide variety of features here, and the things to note is quite a few of these are actually still categorical, so we'll need to run pd get dummies on this. And the other thing to note, if you do kind of a deeper view of the features, this customer ID is actually a kind of primary key or unique identifier. So it's not going to be useful because it's unique for every single row, kind of in the same way this index is unique for every single row. So there's no patterns for this customer ID. So we want to make sure that we don't actually include this as a feature, especially if we run get dummies, it would make 7,227 unique features out of this customer ID. So we definitely need to drop that. So we're going to say here is df drop, and then I also need to make sure I drop the churn label column. So I'm going to drop churn, and I'm also going to drop customer ID, since we're not going to need those. And I'm doing this along axis is equal to 1 because they're columns. So I'm going to say x is equal to that, and then let's create some features out of this. So I'll say x is equal to pd get dummies, and I'm going to say x, and since we're going to put this into a model, we'll say drop first is equal to true. Okay, so next thing I'm going to do is say df churn is equal to my y label. All right, so what we have here now is to perform a train test split. We're going to use 10% of the data for testing, kind of a holdout data set here, and we'll use a random state of 101. Different ways you can do this. We won't really focus too much on running a grid search since we don't want to take too much time here, but again, kind of up to you to try to squeak out some better performance. So we'll say scikit-learn model selection, import train test split, and then we'll say, whoops, train test split here, shift tab, expand on this, and then scroll down until you get to this tuple, and there it is. I'm going to copy and paste this here. Go ahead and paste it in, and then change the test size. So test size, we'll use 10%. And random state, if you want to get the exact random state I have, it's 101. And really, if you want to compare your results to mine, you should be using the exact same test size in random state. That way, your test set is the same as what I'm testing on, so you can fairly compare the models. Kind of the whole point of doing this train test split with a set random state. Okay, so now let's go ahead and start off with checking out how well a single decision tree performs. And what we're going to do is train a single decision tree, and you can do a grid search if you want for optimal hyperparameters. We'll go ahead and just kind of set a max depth of a hyperparameter so the tree doesn't grow out too large. Then we'll evaluate performance metrics from that decision tree. Nothing new, you've done this already. So we'll say from sklearn.tree, import decision tree, and it's going to be decision tree classifier. Make a couple more cells there. Scroll down here as well, center this up. So we have sklearn tree, decision tree classifier. I'm going to say dt is equal to decision tree classifier. Lots of different options we can check out here. You have criterion, splitter, max depth. Since we have so many features, it's probably a good idea to do a grid search for a max depth that isn't too large. I was kind of playing around with a couple, and I'll go ahead and set it to 6. Obviously, if you want the kind of optimal max depth, you can do a grid search for it. There's other things here you can play around with for hyperparameter searching, like minimum samples, max features, etc. But we'll go ahead and just keep max depth as 6 as kind of our one parameter here. Again, not the most optimized tree, but it should perform just fine. We'll say xtrain and ytrain to fit this on. And now we have our decision tree fitted, so it's time to test out how well it performed. We'll say from sklearn.metrics, import, and we're going to import plot confusion matrix. So let's say plot confusion matrix, and we'll also print out the classification report. There we go. So let's start off with a classification report. In order to do that, we need prediction. So we'll say preds is equal to dt predict x test. And then let's go ahead and say print the classification reports for y test compared to the predictions of that decision tree. And so what do we have here? It's performing much better on no churn. And does that make sense? Recall, if we scroll all the way back up, one of the first things we did was check the balance of the classes. And you would expect any model to perform better on the class that has more rows of data. So is this imbalanced or not? It's a little hard to tell here. There is quite a few rows of data for yes. In fact, it looks like there's almost 2,000 rows of data there. So that's not to say there aren't a lot of instances for the models to learn for people that did churn. And we could see that based off our other plots, it was definitely enough to learn what features were important or had high correlation with churning and not churning. So we're going to scroll back down here. So just a couple things to keep in mind as we begin to analyze this with predictive modeling. And scroll back down here. So as you would expect, it's actually performing pretty darn good on being able to spot someone that did not churn. But what about someone that did churn? It looks like it's definitely not performing as well there. And we're getting an overall accuracy of around 81%. But to get a better idea of precision and recall, we can go ahead and plot out the confusion matrix. So we'll say plot confusion matrix. And recall, this takes in your model directly, and then x test and y test. So run this, and you should see a confusion matrix that looks kind of like this. And what we can tell here is that it's misclassifying around 75 incorrectly as saying they're not going to churn when they are going to churn. This is probably the most important thing you want to reduce here. And it looks like we're also predicting that 59 people will churn when they won't. So what's the key error that we should be looking at? Depending on what actions we want to take if we think someone is going to churn, such as give them a discount or give them a promotion, it's not a huge deal to give a promotion or discount to these 59 people who weren't going to churn anyways. What is important is that we actually find the people that really were going to churn. So it's much more important that we find these 75 people versus these 59 people. Because these two are our mistakes, 59 and 75. And probably the 75 is where you're in the most danger of having someone churn, but you don't think they're going to churn, so you don't actually give them any promotion. So given this model, you would essentially be able to figure out 498 correct instances of people not going to churn, 72 people correct instances that they were going to churn, so you could give them kind of a discount or promotion. Same with these 59 people, you give them a discount or promotion, but don't worry, they weren't going to churn anyways. So given this predictive model, you'd probably end up still losing those 75 customers, depending on what capabilities you have in order to keep people that are about to churn. But if you had some sort of 100% way to keep someone on the service and not churn, depending on what actions you could take, even with this predictive model, you would still not identify 75 of those people. Okay. So the other thing we want to do is if you scroll back up here, recall it asked us to calculate the feature importances from the decision tree. That's actually pretty easy to do here. Once you have your model, dt, you can just calculate feature importances and have it report back. However, it just gives you the raw numbers instead of giving you the actual link to the X columns. So what we can do here is set up a data frame called something like important features, and that's equal to pd.dataframe, where the data is equal to dt feature importances, and then the index is equal to x.columns. And then we're going to say that the column names is equal to importance or feature importance. So we can call this feature importance here. Go ahead and run that. And now when we see this important features data frame, let me scroll back up here real quick. You get something that looks nice like this. Feature importance and senior citizen. We probably want to have this sorted. So we're going to say sort values by feature importance. So feature importance there. And let's reset this for plotting. So I'm going to say important features is now equal to the sorted version of it. And that way I can say important features, and I can see a bunch of them that have 0 importance. So whether or not you want to plot these that have 0 importance, kind of up to you. So what we can do here is say important features is equal to important features where, and kind of repeating myself here based off the names, where feature importance is greater than 0. And then I can use this for plotting. So now I have the actual things that were valuable to us. Okay, so how do we plot this out? We can simply say SNS.barPlot, where the data is equal to important features, and then I can say x is equal to that index, and then y is equal to the actual column, feature importance. There we have it. Go ahead and run that. Whoops, this should be important features. There we go. Run that, and there we have it. A little sloppy, so let's go ahead and rotate those x ticks. So we'll say x ticks is rotation equal to 90. And I'm also going to make this a little larger so it's a little cleaner. PLT figure, let's make that fig size a little larger, equal to 14.6, and let's increase that DPI as well. Run that. We can add a semicolon if we want to see those text outputs, and you get this. So what did this decision tree really use to make its decision? It used tenure, and we saw that a lot in the correlation, but there's other things going on here. There's internet service fiber optic. So apparently that's a really important feature that wasn't too clear from our previous analysis of kind of doing all those charts and doing those cohorts. We should be looking at people that are signing up for fiber optics and seeing what is happening with them from a feature perspective. Is that causing them to churn? Or maybe that's a geographical issue where because they don't, or maybe they live in a location where they can't get fiber optic service, so they just decide to change for someone else. Or maybe there's another service provider that is providing fiber optic service. So that's something you can definitely explore further. Monthly charges and total charges and tenure. Recall, these are all kind of highly correlated with each other. The longer you stay on the service, the more tenure you have, which means the more total charges you have, which is also related to your monthly charges. But it's important that you realize these are all connected, but all important features to look at independently as well. And then the final one was optional, which is to plot this tree. We'll go ahead and show you, just to remind you how you can plot a tree. You can say from sklearn.tree import plot_tree, and then from that you just say plot tree, and then you can pass in your model dt, and it will go ahead and plot it out. Now our tree is quite large, so you'd have to save this as a really large figure in order to open it in maybe some other program that we can zoom in. Keep in mind, due to the limitations of Jupyter Notebook, you're not going to be able to really zoom in to read what's going on with this tree. It's also maybe not apparent that it's going to be super useful to have a super large tree in order to make some sort of business critical decision. Maybe just understanding kind of the first few nodes would be more important than understanding the full tree. So just something to keep in mind. Okay, moving along here to random forest, where now our task is to essentially do the same thing, but with a random forest model. So we'll say from sklearn.ensemble import the random forest classifier. And often when you're a data scientist or machine learning practitioner, random forest classifier is kind of the first go-to you have just to get some sort of base performance metric on how well you can expect to perform with this data set. So we can say RF is equal to random forest classifier, and let's go ahead and use n estimators as 100. We'll go ahead and use the default values there. There's other things we can experiment with, max depth, etc. So we'll go ahead and just kind of set it with the defaults and see how it performs, and then maybe we can add in pruning later. So say random forest classifier, I'm going to go ahead and run that with the defaults and say RF fit. Let's go ahead and fit to the train data, and then we'll run some predictions here. So we'll say preds is equal to RF dot predict of x test. Run that, and let's create that classification report. I can actually just copy and paste what we did up here because it's going to be the exact same commands. So let's copy and paste this print classification report because I'm also calling them preds, and we can then directly compare how well the default random forest classifier did. So we run that, and it looks like we're actually performing slightly worse depending on what actual metrics you're looking at. We're getting overall 80% accuracy. If you recall, decision tree up here got 81% accuracy. But then if you look at this, we get 55, 49, 52 on the yes churn. And here we're getting 52, 46, and 49. So it's actually not performing better. What could be occurring here is that this random forest classifier is building the trees too deep. So we could try setting the same limit we set on that decision tree, setting something like a max depth of 6, running that and refitting everything, seeing if that improves it. And you can see that that is starting to kind of tweak your model a little bit so it's not overfitting to the training data. And we can now see we've actually improved the accuracy compared to what we were getting in the other model. And you can see here now we're actually getting higher precision for the yes churn over. The recall has gone down though, but again, kind of a trade-off there, which is probably a good idea to kind of explore this trade-off and then plot this confusion matrix. So we're going to say plot confusion matrix, go ahead and plot RF, xtrain, y test, and this should actually be x test, excuse me, since we want to directly compare its predictions. Go ahead and run that. And now if you scroll down, notice what's happening here, that even though we're getting what looks to be better performance metrics like overall better accuracy and better precision for yes, we want to think, what is the actual problem we're trying to solve here? And really what's kind of critical was this recall. And while we were able to improve everything else by editing things like max depth, for this particular case of max depth is 6 and everything else stayed the same, we actually reduced our recall on yes churn, which means that 75 from the single decision tree now became 86. And as we mentioned before, this is probably the most critical number that you want to be able to reduce. So in this particular case, I would say random forest with these very particular settings is performing worse than a single decision tree. So what then you should be doing here is performing a grid search and testing out a lot more things with the trees within this random forest to see what you can do to actually improve that recall. So if we come back here and run the default settings again, notice our recall is actually still, even with default settings, not that great. But it will go from something like 86 to, let's say, 82, where the single decision tree is still keeping this at 75 for predicted no, true label is yes. Okay, so again, lots of things you can do there. Let's go ahead and finally go to boosting. So we're going to scroll down here to boosted trees. So what we're going to do with boosted trees is the following. We'll go ahead and say from scikit-learn ensemble, import gradient boosting classifier and AdaBoost classifier. Make some new cells here, and let's create an Ada model equal to AdaBoost classifier. Keep everything the default, and then we'll say GB model is our gradient boost classifier. Again, keep the defaults just to do a quick comparison of the two. And Ada model, we will fit it to xtrain and ytrain. And then GB model, we will fit that to xtrain and ytrain as well. And let's create two sets of predictions. That is going to be our Ada predictions or Ada preds. That's going to be equal to our Ada boost model or Ada model. And then we're going to predict based off of x test. And we have those predictions then. Then we're going to have our gradient boosting predictions, which are going to be our GB model. Same deal, predict x test. And now let's actually compare the results. So I'm first going to print a classification report for our Ada boost here. So we're going to say y test versus Ada preds. See what's going on here. Getting pretty good recall compared to other things, and we're getting good accuracy across the board. Let's go ahead and check out gradient boosting classifier. And we'll say print classification report, y test versus our GB preds. And let me scroll up here so we can directly compare these. Run this, whoops, GB pred, singular. Okay, so is this performing better or worse? I would say it's about performing the same. However, it looks like you're getting kind of better recall on just straight up Ada boost versus the gradient boosting. And you're getting better accuracy overall. So given these three models, I would say, let's go ahead and do a plot confusion matrix for adaptive boosting. So we'll say plot confusion matrix, pass in Ada boost or our Ada model, and then pass in x test and y test. Run that and see what our performance is here. And notice now 67 that we're going to churn are predicted that they won't churn. Recall, this is the number we're really kind of most important for us to reduce. And so out of all the models we just tried on the default settings, it looks like Ada boost is performing the best in that particular aspect. And still not super great across any of the models for predicting yes churn. So what can we do to try to fix this further? There's a couple things. One is perform a grid search on what is best for Ada boost. Although keep in mind, Ada boost is not going to have a huge amount of things you can begin to play around with. Number of estimators is one of them though. And we have enough features where maybe that's something we want to play around with. So let's try doing that. We're going to say number of estimators is 100. And what we can also experiment with is trying to play around with your learning rate. For AdaBoost though, it's not going to be a big deal to play around with that compared to gradient boost. So let's try creating more estimators in our adaptive boost model, just doubling it up just to see kind of if that changes anything. So we'll run these predictions again. I'm also running gradient boosting again, even though it's not necessary. And let's check out our Ada predictions. It looks like we're able to perform even slightly better. But again, if we scroll down here, that critical number of recall on yes, kind of staying around the same. So different things you can experiment there, maybe try a grid search, but overall, you can probably see that you're hitting the limits of what's in the data without you possibly resampling the imbalanced class. So just kind of resampling, adding more instances of the people that did churn to give more instances for your model to learn from. You can also try other models like support vector machine classifier or logistic regression and see how those perform given the data set. You can also try performing feature engineering if you have some familiarity in the space. But overall, if you try out these 3 different models and they're all performing kind of around the same, you can just get a general idea of how well tree-based methods are going to perform on this data set. But from what we saw here and just the kind of base parameters we played around with, it looks like adaptive boosting was the best choice for this particular set of constraints. All right, thanks. I hope you enjoyed the project. Feel free to post any questions to the forums, and we'll see you at the next section.